calculate the voltage drop for a three-phase system, a specific formula is used. The formula is voltage drop equals 2 times K times D times I divided by Cm. It is essential to ensure that the formula constants are correctly used, particularly the factor of 2 for three-phase systems. The term K represents the resistance constant of the wire and is measured in ohms per 1000 feet. D is the distance of the wire run in feet. I is the current flowing through the wire, measured in amps. Cm is the circular mils of the wire. The number 2 in the formula accounts for the two current carrying conductors in a three-phase system. K, the resistance constant, indicates the resistance the wire has per unit length. D, the distance, represents the length of the wire from the power source to the load. I, the current, indicates the electrical current drawn by the load. Knowing the allowable voltage drop allows determination of the appropriate circular mils of wire to use for the three-phase system. A larger Cm value means a thicker wire with lower resistance, helping to minimize voltage drop. The constant K value depends on the material and temperature of the conductor. For copper conductors, a common value for K is around 12.9 ohms Cm per foot at its standard operating temperature. For aluminum conductors, the K value is approximately 21.2 ohms Cm per foot at its standard operating temperature. These values represent the resistance offered by a conductor of 1 circular mil in cross-sectional area and 1 foot in length. These K values may change based on the source providing the data. The K value is affected by temperature. Higher temperatures generally increase the resistance of conductors. Therefore, it is important to consider the operating temperature of the conductor when selecting the appropriate K value. Local electrical codes and standards, such as those established by the National Electrical Code, or NEC, often provide guidance on selecting appropriate K values for voltage drop calculations, as well as acceptable voltage drop limits. The NEC provides tables and guidelines for conductor properties and voltage drop considerations, such as NEC Section 215.2 dealing with feeders and 220.19 for branch circuits. These resources help ensure that electrical installations are safe and efficient. To apply this formula accurately, firstly determine the appropriate K value based on the conductor material and operating temperature. Secondly, measure or determine the length of the wire run, ensuring to use feet as the unit of measurement. Thirdly, calculate the expected current flowing through the wire in amps based on the load it will supply. Fourthly, determine the maximum allowable voltage drop based on the requirements of the application and any applicable codes. Finally, rearrange the formula to solve for Cm and calculate the required circular mil area of the conductor. Keep in mind the formula provides an estimation of voltage drop. Other factors, such as inductive reactance, can also influence voltage drop, particularly in longer runs of systems with significant inductive loads. In such cases, more complex calculations may be needed to accurately assess voltage drop. Consulting with a qualified electrical engineer can help to ensure accurate and safe electrical system design. The voltage drop calculation serves as a critical tool in electrical engineering, helping to ensure the safe and efficient operation of electrical systems. By carefully considering all the factors involved in using appropriate formulas and guidelines, engineers can design systems that minimize voltage drop and deliver reliable power to connected loads. Acceptable voltage drop limits are typically set by electrical codes and standards to ensure the proper functioning of equipment and to prevent overheating of conductors. Excessive voltage drop can lead to dimming of lights, reduce motor performance, and potential damage to sensitive electronic equipment. In three-phase power systems, voltage drop can occur in each of the three phases. This can lead to imbalances in the system, which can cause equipment to malfunction or fail. Voltage drop is affected by the length of the conductor. Longer conductors have a higher resistance, which leads to a greater voltage drop. Voltage drop is also affected by the size of the conductor. Larger conductors have a lower resistance, which leads to a smaller voltage drop. Voltage drop is also affected by the current flowing through the conductor. Higher currents lead to a greater voltage drop. To minimize voltage drop, use conductors with a larger cross-sectional area to reduce resistance. Keep conductor runs as short as possible to minimize the overall resistance in the circuit. Use materials with higher conductivity such as copper, which has lower resistance compared to aluminum for the same size conductor. Ensure all connections are tight and corrosion-free to minimize resistance at connection points. Balance the load evenly across all three phases in a three-phase system to prevent excessive current flow in any one phase. Consider using voltage-boosting devices such as transformers or voltage regulators to compensate for voltage drop over long distances. Adhere to the voltage drop limits specified by electrical codes and standards to ensure the safe and efficient operation of electrical equipment. Regularly inspect and maintain electrical systems to identify and address any potential issues that could contribute to voltage drop. The formula given is a simplified version. In cases where greater accuracy is required, especially in long AC runs, it is important to also consider the impedance of the conductors, which includes both resistance and reactance. Reactance is the opposition to the change of current due to inductance and capacitance in AC circuits. To use the voltage drop formula accurately, firstly, ensure that all units are consistent. Convert all measurements to the appropriate units, such as feet for length and amps for current. Secondly, verify the K value for the specific conductor material and operating temperature. Use the correct K value to ensure accurate voltage drop calculations. Thirdly, accurately measure or estimate the length of the conductor run. Use the correct length value to account for the total distance the current travels. Fourthly, determine the actual current flowing through the conductor under normal operating conditions. Use the correct current value to reflect the load demand on the circuit. Fifthly, consider all applicable codes and standards that specify the maximum allowable voltage drop for the specific application. Adhere to the code requirements to ensure safe and compliant electrical installations. Calculate the voltage drop using the appropriate formula, taking into account all relevant factors. Review the results to determine if the voltage drop is within acceptable limits. If the calculated voltage drop exceeds the allowable limits, take corrective actions to reduce the voltage drop. This may involve increasing the conductor size, shortening the conductor run, or balancing the load. Re-evaluate the electrical system design to ensure that voltage drop is minimized and performance is optimized. By following these best practices, engineers and electricians can accurately calculate voltage drop and ensure the safe and efficient operation of electrical systems. Remember that voltage drop calculations are essential for designing electrical systems that deliver reliable power to connected loads. By carefully considering all factors involved and using appropriate formulas and guidelines, engineers can minimize voltage drop and optimize system performance. Proper voltage drop management is critical for maintaining the integrity and reliability of electrical systems. By adhering to established codes and standards, engineers can ensure that electrical installations meet safety and performance requirements. If the calculated voltage drop is too high, several steps can be taken to mitigate it. Firstly, increase the conductor size. Using a larger conductor reduces the resistance per unit length, decreasing the voltage drop. This is often the most straightforward solution. Secondly, shorten the conductor length. Reducing the distance the current must travel will directly decrease the voltage drop. This might involve relocating equipment or power sources. Thirdly, use conductors with lower resistance. Copper conductors have lower resistance than aluminum conductors for the same size, which can help reduce voltage drop. Fourthly, improve connections. Ensure all connections are tight, clean, and properly made to minimize resistance at connection points. Loose or corroded connections can add significant resistance to the circuit. Fifthly, balance the load on multi-phase systems. Uneven loading can cause excessive current in one or more phases, leading to higher voltage drop. Balance the load to distribute the current evenly. Sixthly, use voltage regulation equipment. For long runs or critical applications, voltage regulators can maintain a stable voltage supply to the load. Seventhly, consider parallel conductors. Running multiple conductors in parallel effectively increases the conductor size and reduces the overall resistance. Eighthly, use separate circuits. distribute the load across multiple circuits to reduce the current in each circuit, which lowers the voltage drop. If the application involves motors, reduced voltage can cause them to overheat and fail. For sensitive electronic equipment, voltage fluctuations can cause malfunctions or damage. Consistent voltage levels ensure reliable operation and prolong the lifespan of equipment. Voltage drop directly impacts energy efficiency. Overcoming voltage drop requires more energy, which increases operating costs. Minimizing voltage drop improves overall system efficiency and reduces energy waste. Understanding and mitigating voltage drop are essential aspects of electrical system design and maintenance. By carefully considering all factors and implementing appropriate solutions, engineers and electricians can ensure that electrical systems operate safely, efficiently, and reliably. Correctly calculating the required conductor size is crucial for safety and performance. Undersized conductors can overheat, leading to insulation damage, fire hazards, and equipment failure. Voltage drop calculations ensure that conductors are adequately sized to carry the necessary current without excessive voltage loss. In commercial and industrial settings, voltage drop can have significant impacts on productivity and profitability. Proper voltage levels are essential for the efficient operation of machinery, lighting, and other equipment. Excessive voltage drop can lead to reduced output, increased downtime, and higher energy costs. Voltage drop calculations are a fundamental aspect of electrical engineering and play a critical role in ensuring the safe, efficient, and reliable operation of electrical systems. By carefully considering all the factors involved in using appropriate formulas and guidelines, engineers can design systems that minimize voltage drop and deliver consistent power to connected loads. In residential applications, voltage drop can affect the performance of lighting, appliances, and electronic devices. Excessive voltage drop can cause lights to dim, appliances to operate inefficiently, and electronic devices to malfunction. Properly sized conductors and well-designed circuits are essential for maintaining consistent voltage levels throughout the home. To accurately determine the current, I start by calculating the total power, P, in watts required by the load. For a three-phase system, the formula to calculate power is P equals square root of 3 times volts times I times power factor. We arrange the formula to solve for I equals P divided by the square root of 3 times volts times power factor. Here, volts represent the line-to-line voltage of the three-phase system, and the power factor represents the efficiency of the load in converting electrical power into useful work. For resistive loads, the power factor is close to 1, while inductive loads, such as motors, have a power factor less than 1. Once you have calculated the current, I, in amps, you can use it in the voltage drop formula. When selecting a conductor, consult relevant tables and guidelines such as those found in the National Electrical Code, or NEC. These resources provide information on the ampacity, or current carrying capacity of different conductor sizes and types. Ensure that the selected conductor has an ampacity rating that is greater than or equal to the calculated current I to prevent overheating and ensure safe operation. The NEC provides tables that list the allowable ampacities of conductors based on their size, insulation type, and installation conditions. These tables, such as NEC Table 310.15b16, are essential for selecting the appropriate conductor size for a given application. Keep in mind that the ampacity of a conductor may need to be derated based on factors such as ambient temperature, the number of conductors in a raceway, and the presence of harmonics. Derating factors are applied to reduce the allowable ampacity of the conductor to account for these conditions. For example, if a conductor is installed in a high ambient temperature environment, its ampacity may need to be derated to prevent overheating. Similarly, if multiple conductors are installed in a raceway, their ampacity may need to be derated to account for the increased heat generated by the conductors.